So the first part of this unit focuses on ionic bonds and ionic compounds. And a lot of this is going to kind of come full circle. That we learned a lot about the structure of an atom in the last unit, valence electrons, core electrons. We also kind of brought up this concept of stability, that atoms are stable when they have a full outer shell of electrons. Well, now we're going to focus a little bit more closely on how that's going to happen. How are we going to gain or lose electrons to fill the outer shell and make sure that all the atoms are stable? And so again, stable electron configurations are having full outer shells. Stable because it has a full outer valence shell of electrons. Energetically favorable means low energy is always stable. Now, the only atoms that just come naturally with full orbitals and full outer shells are the noble gases. And so all the other atoms are kind of jealous of the noble gases, and that's why for the most part they're non-reactive. Why would they need to react with anything? They're stable as is. They have full outer shells. And so when we think about most atoms, we're trying to fill the outer S and the outer P electrons. And so in general, we're kind of looking at electron configurations in this way, that the outermost S orbital should have 2 electrons and the outermost P orbital should have 6. N just stands for whatever that outermost energy level is. It could be the 2nd, 3rd, 4th, 5th, who knows? And so we're trying to get then a total of 8 valence electrons. 8 valence electrons meaning 2 in the outermost S and 6 in the outermost P orbital. And we call that the octet rule then, where atoms are trying to gain or lose electrons to fill their outer shell with 8 electrons. Now there is an exception, and that might be little atoms. If you're only trying to fill the first energy level, then we're stable with just 2. So obviously like hydrogen and helium are only trying to fill the first energy level with 2 electrons. And even little atoms like lithium and beryllium might be more stable with just a full first energy level, and that would only take 2 electrons just to fill the 1s orbital. And so there's different ways that we can model this, and we're trying to get an electron structure that looks like a noble gas. And so we could do the Bohr model, where we're showing the energy levels and how many electrons are in each energy level, and there's some good to that, I guess. And we know now that the electrons aren't just flying around in a 2-dimensional circle, that they're really in these 3-dimensional regions called orbitals. But for bonding purposes, and sometimes a Bohr model is not the worst thing, that it just helps us to visualize where the electrons are located. More often, we'll probably use those electron dot structures, where we're only focusing on the valence electrons. I mean, the inner orbitals and inner electrons, the core electrons, they're cool, but they're full, and so they're not going to be involved in bonding. And so these electron dot structures really just show the dots to represent the outermost valence electrons. So we'll do that quite a bit. And sometimes we even go back to electron configurations or maybe orbital diagrams as another way of modeling the electrons. And specifically, we're looking at the outermost electrons. So here in argon, my octet needs to involve the valence electrons. All the electrons in the highest energy level, which here would be the 3rd. And we don't really need to always show the core electrons when we're talking about bonding, because the core electrons will not at all be involved in bonding, just the valence electrons. That's the whole point of bonding. We're trying to fill the outer valence shell. All right, so then we've talked about ions, cations and anions, and here's just kind of a review in that when you look at like the group 1 or group 2 metals, and most metals in general, already have maybe like 1, 2, sometimes 3 valence electrons. And when we try to predict what type of ion will form, will it be a positive cation? Will it be a negative anion? Again, we're just trying to see like what's the easiest route to get to that 8 valence electrons. And so if you already have 1 or 2 or 3 valence electrons, it may be that it's easier just to lose a few, and that might be the best route of getting to a full octet. So for example, like with magnesium, a magnesium atom has an electron configuration 1s2, 2s2, 2p6, 3s2. Well, it's in there, right? 3s2. There's magnesium element number 12. Well, right now looking at my valence shell to be the 3rd energy level, and I'd like to fill it with 8 valence electrons. Right now I've only got 2. And so my options are either lose 2 or gain 6. And what's energetically favorable is always what's going to involve the least amount of commotion. Lose 2, gain 6, we're just going to lose 2. And so it's more likely that we're going to lose the 3s2 electrons, because now my outermost shell ends up being the 2nd, and the 2nd would be full. And so we could model that with an electron configuration. We could model it with the arrows in the boxes, an orbital diagram, or here they've modeled it with a Bohr model. And so I can kind of see, actually the Bohr model and kind of in here would be the little dot structure, right? Normally we'd have 2 valence electrons, they would be in the 3rd energy level, but rather than gaining 6 more, we would just lose the outer 2. And then in the next Bohr model, the one below it, it does show an outer shell that is full with 8. It's just that now the outer shell is the 2nd. Now on the opposite side of the periodic table, once you get over to like the nitrogen family, oxygen family, fluorine, the halogens, now we're talking about atoms that already have like 5, 6, 7 valence electrons. That if I think about a chlorine atom, better give myself some more room this time, right? Chlorine would be 1s2, 2s2, 2p6, 3s2, and then I'd be 3p5. So my outer shell is the 3rd, and overall the 3rd energy level has 7 total electrons, 2 in the s and 5 in the p. I've got 7 valence electrons already, kind of shown here with either the Bohr model or the dot structure. So it's easier just to gain 1 electron and fill that outer 3rd energy level. And then I would have a configuration that looks like a noble gas. And so do you kind of notice that here they're showing me that the ions configuration will look like a noble gas. Magnesium, if I lose those outer 2 electrons, I'm down to 10 electrons. The element that normally has 10 electrons is neon. If I'm chlorine, and normally I have 17 electrons, but I gain 1 more, I'm going to have an electron structure that looks like the nearest noble gas, argon. And so it's important to note that the electron structure will look like a noble gas. Everybody's jealous of the noble gas electron structures. But the nucleus is still a magnesium or a chlorine nucleus. We're not changing the number of protons or neutrons. And eventually then that's kind of what gives us the charge. So if I compare a magnesium atom and a magnesium ion, here's the magnesium atom versus the magnesium ion. The atom had 12 protons and 12 electrons for a total charge of 0. It's neutral. The ion does not change the nucleus. So there's still 12 positive protons, but I lost 2 electrons for a total of 10. That's where the +2 charge comes in. That even when we form an ion, we're not changing the nucleus. So it's not like magnesium somehow morphs into neon. It's just the electron structure that looks like neon. But the core nucleus, the protons that identify the element, that's still number 12, and number 12 is still magnesium. Same thing with chlorine. A chlorine atom versus a chlorine ion. The chlorine atom is number 17, 17 protons, and 17 electrons. Neutral. The ion still has 17 protons, but I gained an electron for a total of 18. So I have a balance of 1 extra negative electron, and then that's where the -1 charge comes from. And so we're not changing the number of protons or neutrons. The charge comes about by changing the number of electrons, and then I kind of look at the balance between the protons and electrons to get the overall charge on the ion. Awesome. So then let's draw a couple. They want me to draw some electron dot structures for the ions formed by nitrogen, oxygen, and fluorine atoms. Use a different colored pen or pencil for the electrons that the atom gained to form these ions. Okay, so here's kind of what we're looking at. Nitrogen. Here's a nitrogen atom. Normally, it has 5 valence electrons. Now, usually we kind of put the electrons around the nitrogen so that they somewhat mimic the orbital diagram. So, for example, the outer shell of nitrogen, well, I guess I could draw all of the orbitals. It's not that big of an atom. If I were thinking about the orbital diagram for nitrogen, 1, 2, 3. So here's the 1s and the 2s, and these guys together would be the 2p orbitals. Okay, so 5 valence electrons. I should say 7 total, 5 valence. Here's the 1, 2, and then here comes my 5 valence. 3, 4, 5, 6, 7. And so the valence electrons are these 7 electrons in the second energy level. And these dot structures kind of mimic the orbital diagram so that we're somewhat accurately reflecting the arrangement of the electrons. And so when I have 5 dots or 5 electrons around nitrogen, we usually do 2 of them paired and then 3 of them single. I know we kind of did this a while ago, but it doesn't matter where you put the pair and where you put the singles. You can put the pair on the top or the sides or the bottom, doesn't matter. But then it kind of mimics the true structure of those 5 valence electrons in that 2 of them are paired and 3 of them are single. If we do the same thing for oxygen, now I would be adding like 1 more electron to my orbital diagram, which would mean that somebody gets paired. And so now there should be 2 pairs and 2 singles. And it does not matter at all where you put the pairs or the singles. 6. So you could put the pairs on the top and the bottom or on the side, doesn't matter. But typically 6 valence electrons would be organized as 2 pairs and 2 singles. And then when you get over to the halogens or fluorine, again, blast from the past, right? Oh my gosh, we learned stuff. We're so smart. You remember those orbital diagrams? Now we would just fill in 1 more electron. And so 7 valence electrons should be organized as 3 pairs and 1 single. So here would be the normal valence electrons in nitrogen, oxygen, and fluorine. Well, we're trying to fill the outer energy level. And so it looks like if we already have 5, 6, 7 valence electrons, we're probably just going to gain a few to fill the outer shell. And so if I use a different color, nitrogen's going to want to gain 1, 2, 3. Now if nitrogen gains 3 more electrons, and electrons are negative, that's going to result in nitrogen having a -3 charge when it forms an ion. Now you could write that as -3 or 3 minus. You might see it either way and it's totally fine. Oxygen's going to want to gain 2 more electrons. And so oxygen typically forms an ion with a -2 charge. And fluorine is going to be looking to gain 1 more. If I gain 1 more negative electron, I will be charged -1. And so that's what we're going to look to do for some of these atoms that are not stable when they're neutral. And stable means having a full outer shell. Neutral just means you got the same number of protons and electrons. The only atoms that are stable when they're neutral are the noble gases. And so here's a good visual of how we're going to try to fill the outer shell.